And then today, my company has a Flow Technical Center, which is specializing only in turbine and compressor oil analysis, which I am going to talk about it today. When you are going to send a sample to an to a laboratory outside your organization, they are going to come back with first a lot of tests which you can do. So they will offer you a package which could be a basic one or then could be an advanced one. And then commercial labs, they work based on more number of samples is better for them. And then they make money based on more number of samples. So there is an algorithm developed by computer. When they test the sample and then the results is known, they come back to you with some off-spec results, you know, sometime by color coding or sometime by trending the data. They come back with the report that sometimes it makes more questions than answering you. How is the oil condition? Is there any problem with the machine? Many people still rely on the reports which are generated by the computer or the algorithm on this oil analysis report coming from the commercial labs, rather than they develop their own knowledge and expertise on the tests, and then how they test it, what they test, and how to interpret the results. So generally with today, half an hour, 45 minutes, I try to talk on the test significance, how important is the test, and what is the method of the test, what are the limits, and then on those turbomachinery, it's very important to rightly set the limits and the targets. And then the different tests when we do and the results they come, which one is more important, and then how to do the diagnosis. And then once the diagnosis is done, what are the corrective actions, how we can improve the situation. This is the whole scenario of the today, half an hour, 45 minutes. So first, let us say the oil analysis starts that you get a test package from oil analysis laboratory from outside of your organization. To develop a Flow Technical Center or an on-site lab, it's very expensive in terms of buying the equipment and as well as having an expert on-site to do the tests. But generally we outsource oil analysis, and then we rely on oil analysis laboratories, which they come back with an offer for the test package. What you see in the right-hand side of this slide is an offer coming from a local lab in Canada for a turbine, and then you see overwhelming number of tests offered in two packages. You know, more tests for them means more money. It's a business point of view, but we need to take care of which test to do, and then how to do the test, what are the methods behind the test, because they are different. And then once the package is known, then we need to do the diagnosis. So first is that to select the right tests to do as per application, because our subject is turbomachinery. We consider turbines and compressors critical, and then including in this seminar, I will focus on these two machines. And then first thing in hand is ASTM standards to look into. Myself, when I started my career in SKF 2009, I started to know about ISO standard 15243, for example, for bearing failure analysis. Then I started to dig into what are these committees, what they do in international organizations, how they make the standards. And today, 15 years I am using the standards. Now I can understand completely what is the picture behind it, because my company today, EPT, is the front, it is in front, and it's a leader in testing of turbine lubricants, and we develop the tests. So let us understand that there is a committee in ASTM for turbine and compressor oils testing, in that committee, there are turbine manufacturers, there are filtration company stakeholders, there are oil analysis laboratories, there are filtration companies. So these ASTM standards, they are not just made in an international office, back in the office. They are made by subject matter experts. They reach to an agreement on the subject. So I'm just not reading the chats. I will come back after half an hour because I have a very short time to transfer the knowledge and experience. So if you don't mind, I will come back at the end of the presentation for the answers. I mean, question and answer. So the first guideline to which test to do is ASTM standards. So as I said, it is an agreement of all the stakeholders about that subject matter. And on gas turbines and steam turbines, there is a standard called ASTM D4378. Latest standard is the year 2020, the year 2020 has been updated, and it is a standard practice for monitoring mineral oils for steam and gas turbines in power plants. So this guideline shows us what to test, how to test, which standard to follow, and then it gives us some recommendations about the analysis and also diagnosis. And then there is one more standard called ASTM D83223, which works on fire-resistant fluids for electro-hydraulic control fluids, for control fluids of power plants. And then auxiliary equipment in a power plant, which are common in oil and gas, in other industries as well. It's mentioned in a standard ASTM D6224. So these three standards are very good guidelines. I can say $60, $70 is maximum price of them. Having the best guideline in front of us, which is an agreement between all the stakeholders, it's a very good starting point making an oil analysis program for an critical asset like a gas turbine or a steam turbine. And then the standard discusses about the recommended tests, what frequency to do, for example, doing it every month or every 3 months or yearly, and then what are the warning and action limits. Warning limit means that if you pass it, you have still time to look into the problem, but the action limit is that you don't need to, you cannot run further. You need to stop the machine and replace the lubricant or find the solution for it. It is very dangerous to go beyond action limits. So it's a very good document to go through it and to see the recommendations, and then even some problems and some analysis and some corrective actions is being recommended here. So finally, if you look at an oil analysis report in front of us, we need to ask questions and we need to get the answers. If we don't get the answers, and this oil analysis report is making for us questions, then it is not really helping us. So the questions to ask is that, will the oil do its job? So it is there to cool the journal bearing, or it is there to operate a servo valve in an hydraulic system. Generally, physical properties, which is the most important, is viscosity, is what we check that the oil is there to do its job. And then if there will be a failure on the way, we need to check the contaminants inside the lubricant. It can be a failure of a lubricant itself, which we will talk today on breakdown of lubricant, which is a chemical breakdown, or the how the lubricant will break down, and then breakdown of equipment. The lubricant can bring data from the component it's lubricating. So looking at the contamination, it's giving the data if the failure is close and how the failure is close, how much is close. And then we need to look at the remaining useful life of lubricant, how long we can still use the lubricant. Once we know about the breakdown is happening, acid number is going high, we have varnish, we have a lot of particles, and then we need to know, once breakdown is happening, how much is the remaining useful life of the lubricant, how much further we can use the lubricant until the first, the maintenance shutdown coming, or the chance of filtering or doing a top up, for example, to make an action, how much time we have. So will the lubricant do its job? First, most important characteristic of a lubricant is called viscosity, and we know about it, no need of going too much in details, but I want to give a recommendation that if you see with 99.9% of laboratory tests which EPT is doing in the lab, most of the time viscosity is in the recommended range, which is plus minus and 10%. But whenever you have a change in viscosity, which is immediate, you have a decrease of viscosity or you have an increase in viscosity, you need to check that if there was a wrong lubricant added to the system. But if the lubricant is dated, it has a long life, you need to check for the end of the life of lubricant and oxidation. Generally, lubricants, oils will be having higher viscosity at the end of the life. And this physical property of lubricant, once it is end of the life of lubricant, and then you pass the limit of 10%, normally you cannot bringing it back to the recommended limits, and then you need to replace the oil. So this is generally two scenarios. When an oil viscosity drops, there is a chance of metal to metal contact, is dangerous. And then if the viscosity is higher than the designed one, you have problems of pumping the lubricant, or even friction inside the layers, between internal layers of lubricant will go high, and then you will have increase in temperature, and then problems of metal to metal contact again happens. So we need to be in the limit of plus minus 10%. When we are talking on turbo machinery, which are mostly ISO 32, which means 3.2 plus and minus plus 3.2 centiostokes, and for a 46 IVG is a 4.6. So it's a very clear cut to do analysis of viscosity, but generally viscosity changes if there is no problem of wrong lubricant to be added as a top-up. Then you need to look at the end of the life of lubricant when the viscosity is going high. And then let's focus of if there will be any issues on the way. So we predict the issues on the from lubrication side by checking the contamination. The contaminants can be particles, can be water, or it can be metals inside. We need to be looking it in 2 points. Some of them are soluble and some of them are soluble. So we need to look at the tests behind them and how to test for each of these contaminants. Let us go immediately to the insolubles, which is mainly particles we are talking now. Abrasive particles, they can come from two sources, from the same mechanical component, internal rated, or they can come from outside of the system. Generally, if they are bigger than the lubrication film, they cause wear and they cause failure. They call starvation, which means maybe the filter will plug because of them, or they can plug a lubrication line. There will be problems of reaching the lubricant to the application. So know all what particles they do, and then there is a very known test behind it, ISO particle count. 3 codes are announced in the oil analysis report. The first one announces the particles bigger than 4 micron in size. Second one bigger than 6 micron in size, and the third digit on the right bigger than 14 micron. The ISO particle count is good in 2 points. Is that first of all, we know the number of particles, it's count for us, and then it's we know the sizes. So one thing we need to know about the particle count, which is important, that 1 digit higher in a particle count, it means 2 times more in that range. So we need to be careful. If the code goes, for example, we have a recommendation here for you. ASTM D4378, which was a standard governing standard for turbine oil testing, recommends for turbines a lube oil system a maximum cleanliness of 18, 16, 13. So we go beyond this, then there will be problems. One code above of these ISO particle counts, it's dangerous. It becomes 2 times more. You see on the right hand side. Now let us focus on the second recommendation, which I am giving. D8323 ASTM recommends a tight tolerance for cleanliness. So let's say cleaner oil is recommended. ISO cleanliness code is 161411 for a turbine electro-hydraulic system, EHC system. It's recommended 161411. And the oil analysis example you see on the right-hand side from one of our customers, it's having 25, 22, 11. So some of my customers, I have seen that they see 25 and above. The target is 16. So it's not nine. It's not 16. They see 16 and they see 25. It's not too much, but it's actually 2 to the times of 9 times more than that. So it is 511 times worse than 16. So it is a very, very dirty oil comparing to the target for that application. One point on ISO cleanliness code that here, for example, we can do an analysis or diagnosis. You see 25, 22, and 11. So number of particles above 4 micron and above 6 micron for this example is out of the off spec or out of the target. So we needed 16, 14. And then 11 is within the limits. 11 was the particles bigger than 14, which means the valve, or in that EHC system, it's doing the job for bigger particles, but it's not doing its job for small particles. So we need to look into a better ratio or improve the efficiency of filtration, and then, or even look into a better let's say kidney loop system to be added to that filtration unit. So we can have an analysis also on the particle count. Let's have a target for each application. ISTM standards for turbines is giving us a good target for that application. And if we have a problem with particles in the system, we need to upgrade the filtration. Sometimes we have an inline filter. We need to look at the filter selection. Most of the filtration companies, they offer upgrades. They'll take the data of the flow and of the temperature, of the pressures in the system, and they, or let's say offline filtration unit. Salah, I'm getting an error. Your connection is slow, it's saying. Do you hear me? Everything is fine?
Beg your pardon? Could you repeat this again?
Everything is okay with my internet. Do you hear me very well? Is it okay?
It was like it's cut a couple of times for just 1 second or so. It's nothing.
Okay.
But yeah, but all going fine. Continue, please. Thank you so much.
Very good. And then you can install a kidney loop skid directly to your tank and then clean up the system so that you deliver. It's very important that for ISO particle counts where we take the sample. Here is out of scope of this presentation, but sampling is also very important to get the good values in ISO particle count. If we get the wrong sample from the wrong location, then these values are not very important. Then second more important contamination is water. Generally, we don't want water to mix with the oil because it doesn't mix. And then if it mixes with water, we have 3 types of water, which is soluble in the oil, and then it becomes, it becomes saturated, and then it can become free water. We have 3 types of water, but the water in the oil, even a small amount, it can corrode the whole system, which the oil is in touch, all corroded. So we don't want any water in the oil, and there are different tests for it. Unfortunately, when we get an oil analysis report, some ASTM standard number is written there, but very few of us, we focus which test is done by the lab. Because, I will tell you 4 different methods of water testing in the oil, and now I will tell you what are their differences. The Carl Fisher titration test is the most precise, which is recommended for whole critical assets to do Carl Fisher. But let's see what are the other.
Sorry, sorry. The sound is cutting. There is
methods.
yeah.
We have a relative humidity RH sensation of the water content. We have a test which is.
Ashar, can you hear me?
I think my internet issue. Is it okay now?
Yeah, the
I can hear you.
wasn't stable for some time, but now it's fine.
Sorry, brother. Sorry for
no, that's okay. That's okay. It's happening, so that's fine. Please continue. Thank you.
No problem. FTIR test is a very simple test. Just in 5 seconds, you can do it in the lab. You put the sample in the machine. It is automated. It gives you even 6 data. One of them is the water content. But the problem with FTIR is that it's not very precise. You repeat it on the same sample, same machine, same operator, on the same lab, it gives you different results. So some tests we call here repeatability is a point that we need to know that some tests, if they are repeated even in the same lab, with the same equipment, with the same operator, the results, they can fluctuate. And they are not very precise data. Even on the same sample, you can repeat the test of FTIR and then you can get water content, which will be a little bit different from the previous results. So we need to know about the repeatability of the different tests and how accurate they are. And one of the other tests which I have seen on $1 million machine like a turbine, some labs are doing, it's a crackle test. Crackle test is simply you put a water on a hot plate, and then once if there is a water inside, then you will hear noise of the water bubbles exploding inside the oil sample. Then this is an on-site test. This is not a lab test, not very precise. You don't want to risk your $1 million machine or turbo machinery to do a crackle test in the lab. For sure, Carl Fisher is the most precise test for water. What are the limits for water? ASTM D4378 recommends 200 ppm for lube oils of turbines, which are mineral-based oils. Not more than that is recommended, because the mineral oils, they cannot they don't have a capacity to keep more than this, and so we are worried about ester-based lubricants, which are used in some of the electro-hydraulic systems like fire-resistant fluid. Ester-based lubricants, some of them they are used in compressors as well. They have a characteristic that they can absorb water from the moisture around them, the air around them, and then they have more capacity to hold. But once it comes in, then it reacts with the structure of the synthetic, and then the process happens. The chemical reaction which happens, it is called hydrolysis. So even they can keep more, but they will be they will be breaking down very fast because of the water inside. So we need to really keep minimum, let's say recommendation is 300. I will talk about dry gas blanketing on top of some reservoirs where we have ester-based lubricants. So we are worried that it is near seaside, so air around the machine has moisture inside. So these oils, they can absorb the moisture in the air on top of the tank and to the oil itself. So we need to be careful about ester application. And then for water, once we identify it in the machine, we need to be carefully finding the source. Identifying the source is the next step. So it's coming inside, we need to rectify that and then fix it. The machines, critical machines or turbo machinery, sometimes they come with a centrifuge or with a coalescer inside. You know, they come with the OEM installation of these machines. Centrifuge and coalescer work based on the demulsibility, based on that the oil has the capability to separate water. Some of the oils, they don't separate water from them. We have a test for it called the emulsibility test for turbine and compressor lubricants. So we want the emulsibility to be there. We can test for it. And then if the emulsibility is good, those centrifuges and coalescers, they can remove the water. If the oil has issues with separating from water, then these techniques, they don't work. The technique which works for all types of water in the lubricant is vacuum dehydration, removes all types of water from the lubricant. And then there is another method which is not that fast like vacuum dehydration, but it's a very good tool to remove some water which is into the lubricant back to the gas on top of the oil. So we pressurize dry gas like a nitrogen on top of the tank, being replacing the oxygen on top of the oil with the dry gas of nitrogen. So we are putting a blanket. We are doing two things here. We remove oxygen, so we slow down oxidation. And then even if there is some moisture inside the lubricant, it can go back to the nitrogen on top. So it's a water removal technology, removing the source of water if it is from the moisture on top, and then even it can absorb water back to the gas slowly. I recommend to go to the APT website. My colleague, Dr. Matthew Hobbs, which is he is an ASTM award winner. He has developed a lot of tests for turbine lubricants to go and have a look at the oil and water shouldn't mix. A webinar on our website. It's a 1 hour very good information on water separability of lubricants. It's mentioned over there. And then we come to the when I talk on lubricants, I don't recall the time. Let me see how much time I have, so I speed up. Salah, I need around 10 minutes more. I finish. Is it okay?
Yes,
10, 15 minutes?
Yeah. Take your time. No problem.
Okay, and then we come to the metals. Some of the rare metals, where they come from, wear of components like rolling bearings or journal bearings, or even in hydraulic machine coming from the hydraulics. The most important are iron and then copper in the journal bearings. We have chromium in the journal bearings. These are the components of rare metals where are important to be checked inside the lubricant. With ICP test, we can check 20 metals in the lubricant. The oil analysis report lists them for us, and then we can know based on how much in ppm we have rare metals, where are the sources, we can know. And then we can have some additives in the lubricant, which calcium, magnesium, zinc. These are very important additives, for example, in anti-wear additives of some hydraulic oils. So we need to put a baseline here. We need to test the new oil to know the metals in the new oil, and then once we test the used oil, so we can monitor the additives, and then we can monitor the wear levels. As I said, automatic algorithms of some softwares with commercial labs, they give you recommendations, but better to go to the ASTM D4378. There is a complete list of whole of the elements with their possible sources. So no need to memorize this, whatever is written in the standard. So myself also, I am looking into the standard. First, I get the baseline sample, and then I look into the used oil analysis. So whenever we are monitoring here by the wear elements, what are how much breakdown is happening in the machine, and then we need to look at the additive consumption. One of the things I do with additives, for example, if there is a turbine oil, and then in turbine oil you don't find zinc, and then I find zinc in the turbine oil, used oil sample. When I do analysis, I understand that there was a wrong top-up of hydraulic oil in the plant, or they were using the same jar or same pump where they are transferring the lubricants and so on. So if there was no element in that new oil and now it is being added, so you can know by oil analysis how the handling of the lubricant lubricant is being done inside the plant, and then let's monitor where, and then how, if for example the iron level, if iron level is going high, you can identify, is it from a bearing or is it coming from outside? If it is a journal bearing failing, you can improve the filtration either with ion exchange, which removes the dissolved metal. So from 20 ppm, 40 ppm iron content inside your used oil, you can remove it. But remember, filtering particles, improving particle counts, or improving the elemental analysis of their elements, it doesn't solve the problem. So once it starts to shoot up, let us not focus on that we are removing it. We need to look at the source. It's being generated, the problem is going on. So improving filtration doesn't solve the issue. So remember that once the filtration removes and you have increased, for example, wear elements, you need to be cautious that you need to improve the situation, you need to do the filtration, but let us not forget the cause, the root cause. And then now let us focus on the fluid breakdown. Once we have either particles, or we have a water, or we have a normal breakdown of which we call it oxidation. Oxidation is the molecules of the hydrocarbon, they are in touch, they are making reactions with the oxygen all the time, and then acids are being created. The most important test historically has been acid number, and then today oxidation byproducts where they accumulate in the lubricant, and then we can test for it how much it is accumulated, how much the lubricant is keeping them inside, how much it is saturated from those oxidation products. We can test for it today, and then the end of the life of the lubricant also can be tested. So first of all, oxidation products are called acids. Acids promote wear, they make corrosion in the system, and even those acids, they are precursors or the starting point of making varnish in the systems. First, they are in soluble format in the oil, and then once the oil is saturated from the oxidation products or those acids, finally they become out of the solution and they go to be insoluble, attaching to the important surfaces of the system. So we need to monitor how much acid we have in the system. So acid can be generated by oxidation, which is weak organic acids. And then on hydrolysis, which some water comes inside, especially on esters, especially of, let's say, phosphate ester or different type of esters, they make strong acids. Why I'm talking on strong acid and weak acid? Because we have heard about total acid number. Everybody has heard acid number and acid number. We need to know weak acid or strong acids are there. It's there in the standard. If you have a professional lab helping you, they can distinguish between weak acids and a strong acids. So I will talk about acidity test, or let's say acid number test. We have two different tests, which I have seen very critical machinery users. They don't care about which test is being done on their oil analysis. We have two tests, which they are identical. They report acid number, but they are different. D664, it's a potentiometric method, which is more reliable. The machine is doing and reports acid number or total acid number, and even it can report strong acid number. So strong acids are more harmful. We can know how much of the total acid number is strong acids, and they are different than the weak acids. And then there is another test called D974, which is based on a visual method. The color change here plays a role. I don't know if you have done it. I have done it with my own hands in the labs. When you do it, it is based on a human or a lab technician to report acid number. When he adds some liquid to the oil, based on the color change, then he reports the acid number. So you know, there can be mistakes, you know, for this test. So I recommend, if your application is very critical, do it based on ASTM D664 only, and no, don't go for D974. It's very important, and very important that you should not compare the results of these two tests. These are the different tests, and then no, we need to tell, if we are giving two samples, or I mean same sample to two labs to check them. There is any problem, Salah? Everything is okay?
Hello, can you hear me now?
Yes, yes.
Yeah,
Everything is fine?
Yeah, yeah, yeah. So far, all good. Thank you.
So ASTM D4378 gives some recommendations for a new oil, or let's say the oil that is not aged. There are recommendations for change of acid number. So 0.1 per year of acid number change, it's considered to be the limit. If you have more, then you need to be worried that the acidity is high in your lubricant. But if your oil is aged, there you have a more tolerance on acid number increase. But you know, the rule of thumb in industry is that nobody is following this ASTM D4378. Generally, labs, known labs, they are taking the new oil acid number, and then once it doubles, then they cut off. You know, they consider that the oil should be replaced and so on. So not only based on acid number the oil is changed, but one of the important tests is acid number. And then you see that the D8323 for synthetics is recommended. How much is the maximum limit of the acid number? So you know, generally the standard is not being followed, but it's a good recommendation to be considered if you want to do the analysis yourself. And then if you feel acidity is going high, the best filtration technique is to use acid filters. Ion exchange technology removes the acids in the soluble form before the oil becomes saturated, and then you will find the varnish in the system and so on. So better to install ion exchange filters from the start of the filling the lubricants, removing acids from the day one, not allowing the acids to combine and to damage the lubricant more and more. So generally there are many acid filters in the market today, but the ion exchange method, which has been tested or used 25 years now in the industry by EPT, it's the most, let's say, reliable method for acid removal if you have a very high acid number with your existing lubricant. So by using ion exchange, you can remove the acids and bringing it back to the spec of a new oil. And then finally, I want to talk about varnish. Once oxidation material in the oil becomes saturated, saturation level of the oil changes with temperature, with flow, and with the pressure. Once it is saturated, then the oil, the physical change happens, and those oxidation material, they come out of solution. They can stick to the valves, which are very critical, to the filters, to the cooler surfaces, and they can cause problems. The known test ASTM D7843, it's updated also by EPT recently in 2021. I am going to talk about the update as well. So the MPC test, Salah.
Yes, we can hear you. There was some cutting and
It's okay.
Yeah, it wasn't stable, but it's stable again now. It,
yeah.
Like, it
okay. With the ASTM,
3-4 seconds, and then it come back stable again.
No problem. ASTM D7843 is checking the varnish potential. Varnish potential means we want to get the oxidation material, which is in soluble format, coming out of the solution, and then we want to put it on the filter patch to check how much saturated the oil is from oxidation material. So it's very important to do it right. I will tell you about the ASTM method, and then out of this patch test, the patch, and then the color intensity of the lube oil sample shows or gives an indication of how saturated oil is from the varnish or from oxidation materials. So the test should be done properly. We need to reset the oil. Resetting means when we take the oil to the lab, we need to heat it at 60 degrees 24 hours, and then 72 hours we need to hold it. These 4 days of testing, heating and then holding it in an area where there is no light, in a closed cabinet, these heating and holding will help that the soluble varnish comes out of solution, it agglomerates, and then you can, when you vacuum, we use a vacuum pump on a filter patch, then we can trap those material on a filter patch. So it helps us to reset and bring out those soluble varnish which is inside the oil. If we don't do that test rightly, in the right professional way as per ASTM standard, you will get low MPC values, which is not, I have seen some filtration companies which they remove only insolubles and they are using depth filtration and so on. They are doing the test on site without following the ASTM standard and showing a very wide patch, no varnish and so on. This is not the right way. Let us do it as per ASTM. And then ASTM D4378 gives delta E values of more than 20 warning and more than 30 as an action point for varnish. The oil is really saturated. But remember, only for gas turbines where you have a high temperatures, you will have very high MPC values. You can get an MPC of 12, but your oil is saturated, and once it cools down, then you will have varnish in the system. This is not a vibration, which is you have millimeter per second and so on as the limit. This is just a potential of having a varnish in the system. The best is that to keep the oil always with the MPC of below 5. So not allowing those molecules of oxidation to stay in the system. So start to remove it from the life cycle from the start of when we put the lubricant in the system, where a varnish removal system which can remove the soluble varnish or soluble oxidation material. This is the best. And then the new ASTM standard tests, just I want to go directly to this slide, where we have a black patch, which is the result of thermal breakdown. Thermal breakdown is different than oxidation and varnish. So thermal breakdown is a result of, for example, sparks or very hot temperature on a journal bearing. You know, the bearing can, you know, the hot spot, they can break down the lubricant into fine carbons. And those fine carbons, we don't see them in ISO particle count, only in the MPC test. When we do it, if we measure the weight of the patch, we can also identify it. And then new ASTM standard by EPT has updated the MPC testing, and it is focusing on the color contributors of that MPC. We don't check only a delta E now. It's the first time by an oil analysis test you can do a diagnosis. Is it a thermal breakdown or it is a varnish? So A and B value shows the, let's say, brownish kind of a color, and then L value shows white and black patch. So if you have a and B which is high, you have a brown patch. If you have a L only which is high, you have a black patch. So distinguishing, you can have a black patch inside the lab, but A and B is low. So you have only black patch, but you know, you can distinguish between, you know, brown can be under the black. So oxidation can be under the thermal breakdown. So you can have a right diagnosis of what's happening with your oil, and then what's the solution. You know, black patch is a mechanical breakdown or mechanical problem, or the brown patch is a chemical problem, which you need to have a varnish removal system. But for a black patch, you need to use electrostatic method, or depth filtration will help, and so on. This is a case study where with electrostatic, the black patch the patch weight also is important, has been removed, and then under that black patch, if it was not rightly diagnosed, they could have mentioned that the first time varnish is high, but black patch delta E MPC could be reported very high, but it is not actually varnish. So it is you need to remove it, and then under it, it becomes to be a brown patch, which oxidation can be under it. So it's a very good update done by EPT on the MPC testing, which it's a new method of doing it. I recommend such a TurboMachinery to be, EPT offers a soluble varnish removal machine, and the first company who invented the ion exchange technology to remove the varnish and oxidation in a soluble format at operating temperature. We don't cool the oil. We are not removing insolubles. We are removing soluble varnish from the oil. So it helps that the oil becomes unsaturated. The oil itself goes to the machine and then removes back the existing varnish in the system. So thanks for your time. I had some slides to talk about RPVOT. End of the life of a turbine and compressor oil sometimes is set by RPVOT values. RPVOT is an oxidation test. We are simulating the working condition of the oil inside the TurboMachinery with the test. And this test works only based on additives, which are antioxidant additives. Once they get used and they reach the 25% of their like they are 100% with a new oil. When they reach to 25%, we say end of the life of a lubricant has reached. This is a very good test, and also in addition to that, there is a test called linear sweep voltammetry, which measures amine and phenol, which are the main antioxidants used in turbine and compressor oils. We need to monitor with LSV the antioxidants used, let's say every quarter, and then once we reach the 25%, it's good to trigger to do an RPVOT to make sure that we are end of the life of lubricant. But we need to be distinguishing that end of, hello?
Yes, we can hear you very well.
That end of the life of the lubricant is not only oxidation. We need to take care of soluble varnish as well. So it can, the oil can have varnish in the system before even reaching 75% of even like 25% only has been used or 10% has been used. Some oils, they become very fast saturated with the oxidation material. So unfortunately, RPVOT or LSV, they don't consider the varnish issue. So we need to do it at the same time. And just about LSV ruler test, which works on the antioxidant levels, and RPVOT, we need to know that repeatability is very poor. It means that you can get an oil tested and get 90% additives left, antioxidants, and the same oil, same machine, same operator, test it again, and then it jumps up to the 95%. So you need to be trending the data, and if they're like 2-3 months in a row, the antioxidants were dropping, then this is a good one. This is not an error with the test. So we need to be careful that not to focus on RPVOT and then LSV or ruler test values. We need to trend the data to be sure that we don't have any jump up and down. So the best turbine or compressor oil maintenance today is that to install a soluble varnish removal machine from the start, manage oxidation, don't allow the antioxidants to get used very fast, and then no need of adding any chemicals. We don't recommend, we don't interfere with the job of Total, Shell, and they know best what is the additives required for the oil. So let us do the top up whenever required and use the soluble varnish removal to manage oxidation and acids inside the oil, which can cause problems. Final consideration is that when you are doing a test, remember about repeatability. And what is repeatability is the same lab, same equipment, same test. It has some errors. We need to know it. And if you are doing it with different labs, reproducibility is important. So it means that the test being done by a different machine, different operator, a different lab, it can have some errors. So be careful. You can ask your lab a certain repeatability to be acceptable for a certain test. This can be done for critical machines. And then remember about the, for example, acidity. We discussed about the total acid number, the different tests, which was the titration, Carl-Fisher or FTIR. Don't compare the results of different tests, do the right test. And then I recommend using the very professional lab of EPT, which is in Canada. Many oil samples from around the world from TurboMachinery are being sent to the lab. Our lab is not a commercial lab. We focus on TurboMachinery, and we develop the test. It's an R&D lab, which we can support you. As a summary, will my oil do the job? We need to check the viscosity. Is there any failure on the way? Check the insoluble particles, check the water content, check the metals from the new oil and then used oil. And then, is any future problem coming? Check the acid number, check the varnish potential. And then how long the oil will last in my TurboMachinery? Will it make to the next shutdown or the maintenance interval coming? Use LSV as the antioxidant levels and use the RPVOT. This is my last slide of today. I tried to be very quick. The subject needs a minimum 3 hours, and thanks for that. I hope the success I had in Oman with many turbines and compressors. I supported PDO, one of the biggest oil and gas companies in our region. And then thanks to Salah Atiya for a very good opportunity to do this recording, inviting you. I'm always available with my email, and I'm in my LinkedIn account. We at EPT, we specialize in turbine and compressor oil maintenance, hoping that you come back to me. Thank you very much.
Thank you very much, Hashar. That's really was an amazing presentation. And exactly as you say, that was going to take hours, not just like 45 minutes would be enough. Yes, you go fast through the things, but you was also precise, and you mentioned many detailed things. And if anyone, as you said, want to go into more details, he can reach you. And thank you very much for this
if you can
presentation.
ask people to come up with their photos, we can make a group photo. That would be very good.
Yes, excellent. Yeah, if you can, everyone, if you can please open your video camera and let us have a photo. That would be great.
Oh, I see Gift Mukaba from Zambia. Very good, my friend. Oh, very good. Very good, very good. How many are there in the photo? I don't see the full photo.
Like we reached around something like 48 participants, but you cannot take more than this. Like
it is a working day anyhow. I didn't answer the questions, so let me read the chats if they are there.
The questions I will as I did with all other presenters, the question will already copied, and I will send it to you by email. Then you will answer these questions and you put it in post on LinkedIn.
Sure, sure.
Okay, everyone can smile. Excellent.
Okay, thanks everybody. Tony, thank you for coming, Saudi Arabia. Tony, thank you.
I will save it.
Thank you very much.
Saved.
Hoping it was a useful session for you.
Thank you very much. Thank you, everyone. See ya.
Bye-bye. Thank you.
Bye-bye.